You know, I haven't really been recently talking to you guys that much. I mean, like, I wish I had a face cam so I can connect more, but I don't have a face cam. I don't think they're necessary. I don't think it's too necessary. But I haven't been talking to you guys much. I had like in Calculus 3 when I was making the Calculus 3 videos earlier this summer. I didn't make. I just literally for the first minute of the video I would just talk to you guys about some random thing that's going on in my life. But I guess the random fact I'm gonna give is that I have like a bro. I was cooking eggs like 2 weeks ago, and my wrist touched like the corner of the pan. Okay, and it branded my hand, so I got like just a straight line across my forearm right now. And it looks like a brand mark. So that's the interesting fact. But hence the what you're seeing on the screen right now. You're seeing sort of an example of how to solve for an antiderivative using U-substitution. But this time it's a definite integral. So I'm going to show you a general way to solve this. Of course, you can skip the general way and just go straight to the problems, because that's probably going to be a lot more helpful rather than seeing all the numbers and stuff like that. But basically, the general formulas I'm going to show you. Maybe if you're a math person, you like looking at math notation, this will be helpful, but it's not. If it's not, just skip to the problems right now. So when you're trying to find your new bound after you substitute for u, you have to plug in b into your function of u in order to get your new bound b. Because if you just use the old bound b and the old bound a, you're going to get a wrong answer. You need to replace the upper and lower bounds after you substitute with u. And in order to do that, in order to find the new upper and lower bounds, you simply need to plug in b into your function of u and a into your function of u as well in order to get the new upper and lower bounds. But let's go on some problems. This will probably help you visualize this and understand it more. So, of course, when you start off with any U-substitution problem, you have to recognize it's a U-substitution problem first. So, if you look in this problem, is any factor in this the derivative of another factor? Well, x is some derivative of x squared, some variant of some derivative of x squared. So, x right here is your derivative of some inner function. And what we want to do is set the inner function equal to u. Okay? And then when we solve for the derivative of both sides here, you solve for the derivative of u, you get du. You solve for the derivative of this side, you get 2x dx. And again, if you isolate dx, you'll get du over 2x. So right now we have x times u cubed, right? Since u is equal to x squared plus 1, we can substitute that in. And dx is equal to du over 2x. So du over 2x. Now, keep in mind, you want every single variable to be in terms of u, including the differential, du. So you don't want a dx here. You want a du, and you want everything else to be with the variable u. Right now, you see variables x, right? This is not good. But in this case, you can actually cancel out the x's. So your integral gets left off as 1/2, since I factor out the half at the bottom of this du out, times the integral of u cubed du. Now this is the good part. This is the part where it's different than solving just for an antiderivative. You need to plug in your old bounds into this function here. So you can plug in your old bounds 1 into this. So if you plug in 1, your b of u is equal to 1 squared plus 1, which is just equal to 2. And your new lower bound is equal to a of u, which is just 0 squared plus 1, which is equal to 1. Therefore, our new integral bounds are 2 and 1. So if we take the integral of this, we get 1/2 times u to the power of 4 over 4 from the bounds 2 and 1. So this notation right here, if you see this, this is if you see closed brackets actually. I guess it doesn't matter too much if you have open brackets or closed brackets or angled brackets. But this notation just states the bounds of your integral. So right here, if we plug in 2, we get 1/2 times 2 to the power of 4 over 4, which is simply equal to 4. So we have 4 here minus 1/2 1 over 4. And all this equals 2 minus 1/8, which is equal to 15 over 8. So this right here is the right answer. Now, you can also solve this another way if you're lazy and you don't want to find the new bounds, right? You can replace your u value or your antiderivative with the original function. So if I wanted to simplify this, you have 1/2, and the antiderivative is 1/2 u to the power of 4 over 4. So we'll replace u with x squared plus 1 again over 4. And instead of using the new bounds 2 and 1, these bounds are in terms of u, by the way. Right? In terms of u, you want to use the older bounds 1 and 0. So if you turn everything back in terms of x, then you can use 1 and 0. But if you turn everything in terms of u, you have to use 2 and 1, or the new bounds that you calculated by plugging in the numbers into this equation. So if I were to solve for this, this would be 1/2. If you plug in 1 into here, you would get, oh, this is to the power of 4. If you plug in 1 into here, you get 1 squared plus 1 to the power of 4 over 4. Minus, now I have to make more space for this, jeez. Minus 1/2 0 squared plus 1 to the power of 4, of course, over 4. Now if you simplify everything in this equation, it all just equals 15 over 8 as well. So you can do it in both ways, but make sure if you want to plug in the numbers into your u value, you have to put it through have to put it through this function, your u function, in order to get the new bounds. So both ways works, right? Each of these are equal to each other, but the bounds must be changed in terms of x or in terms of u. Now you might be wondering, well, if there's no point, if you get the same answer, if you just replace everything with x, what's the point of learning this? Right? What's the point of setting your integral in terms of u? Well, in AP Calculus, when I took it, there were some problems that literally just told you, make this integral in terms of u. Don't even solve the integral, set the integral in terms of u. So, that's that. So that's why I'm making this video. That's why I literally just came up with it on a whim like a second ago. But let's go ahead and solve for this. Well, what is some derivative of something else? Well, ln of x times 1/2 times 1 over x, is equal to this. Correct? Well, 1 over x is some derivative of ln of x. So ln of x is hinted at us some form of an inner function, right? Inner function in your chain rule. So right now, u is equal to ln of x. du 1 over x dx. That's what we have. And if we isolate dx, we get x times du is equal to dx. So if we rewrite this integral, you get the new integral u over x times x du. The x values cancel out, and you get the new integral u du. Now here's the thing. We want to find the new bounds of this. So if we plug in 1 and e into this function, we get, so b of u is equal to ln of 1. Let's put a parenthesis over that to make that clear. Sorry, b of u is equal to ln of e, sorry. And a of u is equal to ln of 1. So ln of e is 1, ln of 1, any logarithmic function of 1 is just equal to 0. So your new bounds are 0 and 1 in this case. So if I wanted to solve for this antiderivative, we'd get u squared over 2 with your bounds 1 and 0. So we plug in 1 and 0 here, we'd simply get 1 over 2 minus 0. So our answer is 1/2. Now, let's solve this problem in terms of x now. So this is our antiderivative, u squared over 2. So if we replace u squared over 2 with your x values, you get ln of x squared over 2 with the bounds 1 and e. So if we plug in e into this, we get ln of e squared over 2 minus ln of 1 squared over 2. And natural logarithm of e is just 1. 1 squared is just 1/2. And natural logarithm of 1 is just 0. 0 squared over 1/2 is just 0. So our answers are both the same. It just, we solved one in terms of u and one in terms of x. So for this problem, it immediately stands out to us that the inner function is equal to 9 minus x, right? It's just something being square rooted. That's like the only inner function that you can set equal to u. And don't worry about this dx. dx is just, see, you could treat dx as just some algebraic entity, and if you just multiply dx by some fraction, it goes into the numerator. So this is just normal integral notation, and what we can do is take the derivative of this. We get negative dx. If we move the negative onto the du side, we can isolate dx, and we can rewrite this integral so that you have 1 over the square root of u, technically negative 1 over the square root of u times du. And the negative comes from, remember, the negative in the du part here. Well, how do you find the bounds? Well, if you want to find the bounds, then you must plug in the number 4 as the upper bound and the number 0 as the lower bound. But why is this weird? Well, your upper bound is actually greater than your lower bound. Don't worry, not that bad. If we flip over the bounds, all we have to do is multiply our integrand by negative 1. And if we multiply our integrand by negative 1, you get positive 1. And this negative kind of goes away. So remember, if you flip the bounds, just multiply your integrand by negative 1, and your answer will still be the same in the end of the day. So now that we have the numbers in order, we take the integral of 1 over the square root of u, which is just 2 times the square root of u. And the bounds can be written like so, 9 and 5. And keep in mind, even if you have these closed brackets, it just means the same thing as the straight line. That just gives us the bounds, and this is our antiderivative in this case. So if we plug in our bounds, we get the square root of 9 minus 2 times the square root of 5, and this simplifies equals 6 minus 2 times the square root of 5. So really, again, you can just solve this in terms of x, but in this problem we solved it in terms of u using the bounds that we got for u. But, as always, if you have any questions, put it in the comment section. This was my second time recording this problem, so it's kind of annoying, but if you found this video helpful, consider subscribing, and liking the video. Thanks for watching.